We're starting section 14.8, Lagrange multipliers. First, we discuss identifying extrema on a boundary using Lagrange multipliers. That's something that we basically can do for the closed and bounded sets also. In one of the ways that we use Lagrange multipliers, and then we can do multiple Lagrange multipliers when there are more than one constraints. So let's talk about a typical constraint optimization problem. Find the maximum value of f of x and y equal to x times y subject to constraint x squared plus 4y squared equal to 16. Note that the function f of x and y equal to x times y, we're trying to find the maximum of this function over the effective domain x squared plus 4y squared equal to 16, which is an ellipse basically. And so we're restricting our domain just to that ellipse, which is a curve. Now, what you have to notice is that not if you find the critical points for the function, those critical points may not live on or be on the ellipse, and in this case they are not. And so when you find a gradient of f of x and y equal to y and x, the only critical point is going to be 0 and 0, which is not on that ellipse. And we're not basically looking at that critical point at all, because we're just looking at that effective domain, the new domain of the function. And so the good thing about this new domain, the blue ellipse, is that it's closed and bounded. And so by the extreme value theorem, there has to be a local max and local min on this ellipse. Now, let's look at the how the level curves of this function are. So the red are the level curves, and the constraint, the ellipse, is shown in blue. If in this case, I know that the function has has absolute min. I'm sorry if I said local in the previous page. Absolute min and absolute max on the ellipse because of the extreme value theorem. And so, looking at this picture, I see that so the level curves are basically getting bigger and bigger on the first quadrant, level the values on the function on those level curves gets bigger and bigger as you get away from the origin, and the values on the second and fourth quadrant, because those are basically the same piece, the different pieces of the same level curve, each pair it is, they're getting smaller and smaller and going to negative. They're just bigger and bigger negative values as you get away from the origin over here. And so if I'm looking for bigger and bigger values of f on this ellipse, I'm going to look as far as it can go on those level curves. And it happens that, and I'm looking at this and I see, oh, the blue curve and the red curve have to be tangent to each other for function to have the maximum value on the blue curve. And over here also tangent to each other to have that's the minimum level curve that it can touch, basically the blue curve can touch. And so this is why the the level curves have to be tangent to the constraint, basically, if the absolute min and absolute max exist. So let's talk about this because we gave an example. Now let's talk about it more generally. Objective: find the extrema of z equal to f of x and y subject to the constraint g of x and y equal to k, where k is a constant. So let's say f with different values, with different level curves, and then g doesn't have to be always closed and bounded. And let's say g is like this. Just looking at this g, when at what value, at what point on g does f achieve the maximum? At the point that the g of x and y is equal to k is tangent to the level at the highest level curve, basically, that it touches. And so that's the point. And so this is another way of looking at it. And so let's g of x and y equal to k be a constraint curve C. Then suppose P of A and B is a local extremum of F on C, and F of A and B is equal to M. And then what you see at A and B, the level curve f of x and y equal to M is tangent to C. So you can see clearly at P, f of P is equal to 7. And so f of x and y equal to 7 is tangent to C right there. So what happens at the point of absolute min or absolute extremas is that C is a level curve of g of x and y. Therefore, the gradient of g at A and B is orthogonal to C. Also, f of x and y equal to M is tangent to C at P. So the gradient of f of A and B is orthogonal to C. Now, I found these basically two different vector orthogonal to C, so they have to be parallel. So the gradient of f at A and B is parallel to gradient of g at A and B, and that's one way of looking at it. This is one way of explaining how the Lagrange multipliers work. I haven't even explained to you what that is, but soon you'll see. And then let's talk about another method of seeing this. So let's first explain Lagrange multipliers. Assume that f of x and y and g of x and y are differentiable functions if f has a local extremum on a constraint curve, g of x and y equal to k at P, A and B, and if gradient of g at A and B is not a zero vector, then there exists a scalar lambda such that gradient of f at A and B is equal to lambda gradient of g at A and B. That means that the two gradients are basically parallel because one is the scalar multiple of the other. We're going to discuss how this works in practice when you're trying to do examples. Before going there, I want to say that there is a little proof in here for you guys to read if you want to look at the notes. It's the technical proof of the picture that we shown in the previous page, basically. And so you can use this to understand the proof of the theorem, basically. Okay, so how does the Lagrange multipliers work? the method of Lagrange multipliers. To find the extrema of z equal to f of x and y subject to constraint g of x and y equal to k, first find all the values a and b and lambda such that g of a and b is equal to k, and gradient of f at a and b is equal to lambda gradient of g at a and b. So this is total of 3 equations and 3 unknowns. And so what you because each, when you're setting a gradient to another equal to lambda times another gradient, each gradient has 2 components, and so it makes sense to have 2, that it does have 2 equations just by setting the 2 gradients equal to each other and setting the values inside the basically making sure the constraint works on those. That's another equation. And then you have unknowns that are a, b, and lambda. Often the best way to solve this system is to start by eliminating lambda, because lambda is not important to us. Lambda just shows that the 2 of them are parallel. What is important to us is a and b. So if you can't eliminate lambda, just get rid of it and try to work on a and b. Calculate the values of f at all points a and b. That's step 2. All the values a and b found in step 1. Then check to see the largest of those are absolute maximum value, smallest of those are absolute minimum of f, if they exist, basically, by on the constraint, the values of f constrained by g of x and y equal to k. The same method works for functions of 3 or more variables. So an example. Example 1, and this is for Lagrange multipliers of 2 variables. Suppose that 2 positive numbers have sum 12. How large can their product be? So we're saying that 2 positive numbers, and this seems like a constraint to me. So equal to 12, and then we're looking for the product, which is a function of x and y, to be x times y. So that's the constraint, that's the, and this one is the function. Now what you need to do is, first of all, there are 3 equations. 2 of the equations have to do with the gradient of p and gradient of g. What we do, we have to be careful, is this. This one is g of x and y. So gradient of p, gradient of g is going to be 1 and 1. Gradient of p is going to be, looking at this, it's y and x. So set all the equations. One of them and 2 of them are related to basically gradient of f equal to lambda gradient of g. What does that do? It says gradient of p is equal to 2 arrows and it has to go. Gradient of p equal to lambda g. So y equal to lambda, and then x equal to lambda are these 2. And then the last one has to be x plus y equal to 12. Now, to be able to solve, I first, in the 2 equations related to the gradients, I eliminate lambda, and from that I get x is equal to y. Now I plug in for y, I plug in x, and what we get from here is 2x equal to 12, that is x equal to 6, and then y has to be equal to 6 also, and the only point that we got is x and is 6 and 6. So the next question is, so I got one critical value on the constraint, but what is the constraint? Constraint is not just x plus y equal to 12. It's x plus y equal to 12 and x and y bigger than 0. So let's just figure out the value of the function on the two endpoints here and 6 and 6. So 6 and 6, 0 and 12, and 12 and 0. These are x and y. Then find f of x and y. Now this piece is closed and bounded, right? And so if I plug in back to of the x and y, I get 36, 0, and 0. And that is the maximum value that you can achieve. Suppose that you want to use the method of Lagrange multiplier to optimize f of x and y equal to 3x plus 4y subject to constraint x squared plus y squared equal to 1. Which of the following equation is not part of the system of equations you need to solve? Give yourself a minute and then come back. Okay, so you probably solved this question by now. You want to find gradients of f, which is going to be 3 and 4. Then you want to find gradients of g. Where is the grade g? G of x and y. And gradient of g is going to be 2x and 2y. So all the equations are, let's say 3 is equal to 2x lambda, 4 equal to 2y lambda, and then the equation that is given already, you have to solve this. So let's see which one. So one of them is A, one of them is B, and the other one is C. D is not part of those equations.